So last time we talked about that we want to even reduce the bandwidth for AM signal. So that comes the third one in this family, single sideband. Okay, we mentioned last time, no matter you have upper sideband only or lower sideband only, you can recover original signal. So it means one sideband is sufficient, right, for our information transmission to the channel. Therefore, we can just transmit one sideband. The straightforward method will be using sideband, like sideband filter. However, for some other cases, it's really hard for us to get an ideal right sideband filter. We show some examples. What is a real filter we use, right? What are the real life filters, like buttonless, shape-shift, elliptic filters. So for some signals, they are pretty close with each other. We cannot use sideband filter to remove one sideband. What can we do? Today we talk about second method. We call it phase shift method. Okay, so we use sinusoid as our message. Try to make our analysis easier and simpler. So we look at our signal and try to find the tricky thing inside. Then we can build up our method to generate single sideband. My message sinusoid. Listen to my carrier. So double sideband signal is message and carrier, right? Okay, now the tricky things come. So cosine times cosine, we have cosine, the summation of the two phase angles and the difference of the two phase angles. So if you look at this one, so this one is my upper sideband, right? Transform of cosine of MT. So this is the Fourier transform of cosine omega MT cosine omega CT. Okay, so here, upper sideband. So cosine omega C plus omega M, right? Those two impulses are my upper sideband. Any problem? Second part in this equation. Is my lower sideband. So lower sideband. Lower sideband. In the slide, we use SSB plus for upper sideband, right? SSB minus for lower sideband. So here for this cosine omega C plus omega MT, if you check your table, the cosine alpha plus beta, we get cosine alpha, cosine beta, right? Minus sine alpha, sine beta. So we have upper sideband be written in message, carrier. This one is modification of my message, right? This one is my message with a phase shift. How much we shift, right? 90 degrees or pi over 2. Sine omega ct is your carrier's phase shift by 90 degrees. Okay. Any problem for this one? Hair to hair, we use equation in a table. And when we look at this one, we can see we have 90 degree phase shift, both for message and carrier. So this is what happened for my upper sideband. For lower sideband, we're going to find similar things. So for lower sideband, we have cosine omega c minus omega. So we have cosine times cosine plus sine sine. Okay, here my message, right? My carrier. My message with a shift. My carrier with a shift. So we get lower sideband. Okay, now we change this very special sinusoid signal into a general case. So for general case, single sideband can be obtained by message times cosine plus or minus with the message with a phase shift. Okay, later we talk about why there is a hat and carrier with a phase shift. So we call this one phase shift method. If we choose plus sign, we get lower sideband. If we choose minus sign, we get upper sideband. So both information and the carrier shifted by 90 degrees. We combine them together. Again, we get either upper or lower. So for sinusoid, this is a picture show what's going on. Okay, so analytical generation of single sideband. This is for upper sideband. Okay, now we have so this is method number 2 for generating single sideband. Similar as our equation, right? We have signal mixed with carrier as one branch. Another branch, signal shifted, carrier shifted. So at hat of t will be mixed with sine omega ct. We use plus or minus. We get upper or lower. So this is block diagram for method number 2. In this case, even you have your two sideband are pretty close, right? We still can generate single sideband. now we're going to talk about why there's the hat. Okay. So we use Hilbert transform to explain what's going on when you shift it. Your signal space by 90 degrees. After you shift it, right, we call it x hat of t. This is the mathematical equation how we get Hilbert transform in time domain. In frequency domain, we can model this whole entire transform as signal past a system. So for this kind of transformation, my magnitude does not change at all. However, my phase shifted by 90 degrees. Let me see if I have the upper in this slide, we show the frequency transfer function for Hilbert transform system. So this is a picture for Hilbert, and it also explains where there's a hat. There's a hat. So there's a hat, Hilbert transform, and what did Hilbert transform do? Right? Just change your signal phase by 90 degrees. So this is the frequency transfer function for Hilbert transform. We can find magnitude, right? There's nothing change for your magnitude. However, phase, right? When your signal is negative, when your frequency is negative, we have power 2 phase shift. Positive, we have 90 degree phase shift. Okay, so we talk about, right, how can we get single sideband. Here we try to go. So we try to prove using frequency phase shift method, we can generate single sideband. We prove when xt is cosine omega m of t. Substitute xt into equation number 1, right? So we have cosine minus plus sine. Now go to the table, we get my answer will be cosine omega c plus or minus omega m of t. So plus we get upper, right? Minus we get lower. Any problem? So here, as when my message is sinusoid, right? We prove we can get upper and lower sideband. Now, since the entire transformation is linear modulation, so circulation holds for other signals, not only for sinusoid. So we have two double sideband circular carrier added together. We can get one sideband cancel, get another sideband. So this is method number 2 for generating single sideband. Okay. Any problems, any questions? So we are we finished talking about single sideband transmitter part. Now, receiver part. Oh, okay. Actually, this one is the same, right? This one is the same. Yeah, this one is same. This so we have two carriers. Two carriers, they have different phase. Previous one, we have one single carrier. We use two phase shifter, right? This one we just use one phase shift. It's also common in QPSK, right? And power manipulation. We have two orthogonal carriers. So this one pretty much the same as previous block diagram, and also follow the equation we mentioned. Okay, now, exercise. Okay, so I give you like 5 minutes. Try to draw the phase of single sideband wave, and the message here is sinusoid. Okay, so try to play with it, and later I give you some hint. phasor for double sideband suppressed carrier, right? So we have, what is this one? This is my upper band, right? This is my lower band. So upper band is related with this vector, right? This is the phasor for upper sideband. This is phasor for lower sideband. So if I ask you to plot the single sideband phasor, there will be only one vector, right? Either this one for upper or this one for lower. So for this exercise, so only one, right? Only one will be my upper or lower. Two of them, double sideband suppressed carrier. If I add another phasor over here, it will be large carrier. Okay. This one, phasor will be either like this or like this for upper and lower. Next one, I'm going to use this one as an example of exercise. For double sideband large carrier, double sideband suppressed carrier, we sketch the time domain waveform. For single sideband, generally the waveform will be very, very complicated. However, for some special case, we can still plot the single sideband, for example, like this. So, sketch in time domain, right? So we have cosine. This is my message. Right? This is my x of t. This is cosine c of t. So if x is a general case, very complicated and not required. However, for this one, we can rewrite it as so for upper sideband, right, my message should be half. I can just plot a sinusoid, right? Sinusoid. Okay, the period for my upper sideband will be 1 over Fc plus Fm. So here will be 2 pi over omega c plus omega m. Omega c we know is 10 to 6, right, times 2 pi, and omega m is 10 to 3. This is my upper sideband. Lower sideband still have the same amplitude, but Fc minus Fm. So I'm going to still have sinusoid signal, but the frequency is lower compared with upper sideband or your carrier frequency. Omega m. So this will be the only case if I'm going to ask you to plot the time domain waveform for single sideband. Only when you message is sinusoid. For other cases, sketch by hand is really difficult. If you really want to know what's going on, you can try to use MATLAB to show the waveform. So for double sideband, large carrier, suppressed carrier, single sideband, we show the phasors, right? Sketching time domain, sketching frequency domain. Yeah. So I believe we can finish this lecture. Now, any problems, any questions? Now we go to the receiver side. How can we demodulate a single sideband AM signal? So similar as suppressed carrier, we use coherent receiver or synchronized demodulator. No matter you have upper or lower sideband, we mix this carrier, goes through low pass filter, we get our original signal recovered. So this is example, we have upper sideband. So for upper sideband, mix this carrier, right? This one move higher and in the higher frequency. Same thing. So this upper sideband move to higher and over there. After low pass filter, the high frequency parts are gone. Only this one left. So even single sideband carry all the required information for the demodulation. So the same as suppressed carrier. If we have lower sideband only, right? And last time we showed lower sideband. So transmitter shift your frequency, shift your spectrum up, right, by carrier frequency. Demodulator shift them back, right, omega C of C, so we get a signal demodulated. Okay, so this one is important. We use coherent detector to get my information from the carrier. The message, the carrier should be the same as your transmitted signal's carrier. And how about the low pass filter? Low pass filter should be good enough, right, to cover all my spectrum in the desired area and remove the other ones, right? The other ones. So when you design your receiver side, you should determine what is the reference signal you use and what will be your low pass filters bandwidth. Okay, two things. Okay, this is the last one for this class. So I want to design a demodulator for this signal. So number one, what is my signal? Yeah, this is single sideband, right? Single sideband. And can means upper sideband or lower sideband. Plus sign means opposite. Lower sideband. So for single sideband, we use coherent detector, right? Coherent detector. We need to figure out omega C and the bandwidth. Okay, so this one, let me show you. Then I'm going to stop. So based on the equation, in 360, if you find this hat, right, you remember Gilbert, and this is for single sideband. So we have lower sideband, right, signal. Question mark for reference, question mark for low pass filter. Okay, this one is very close to your homework number 4, problem number 4. So according to the previous structure, as we know, this one should be cosine omega C of t. And my cutoff frequency of your low pass filter should be good enough, right, to cover my signal spectrum. And we know that my highest frequency of my message is it's W, right? It's W. So omega C should be at least either same or higher than W. So let me write down here. We use cosine 2 pi into 6t. This is my reference based on the given condition. And this is my low pass filter. Your cutoff frequency should be at least higher than the bandwidth of your message.